Hello, good morning. Yes, I would be able to see this is our clip 005. For doing this clip, I would like to just briefly remind you what we have been learning about the QM models. For the QM model, this is a very a complicated concept, but even though it's complicated, but doesn't mean that we need to remember a lot. Basically, the most important thing you need to remember for QM model would be how do you write down what we call the electron configurations. Electron configurations would be in the previous model, we call them Bohr model, which is very easy. If you have a sodium, you can write down as a Bohr model electron configuration is 2, 8, and 1. So I try not to explain this anymore, but like you should be able to know why we put Bohr model as 2, 8, and 1. However, if you try to look at the QM models for sodium, it may not be 2, 8, and 1 anymore. We have to write this one down. So instead of 2, 8, and 1, you will see the QM model for sodium is 1s2, 2s2, 2p6, and 3p1. Um, you would be able to resemble this one with the Bohr models as when n equals to 1, it only has one subshell. When n equals to 2, it has two subshell. N equals to 2 would be has a number 2 in front of it. When n equals to 3, you expect that you should have 3 subshell. Sorry, not p. There's something wrong here. There's supposed to be 3s first, 3s1. And we have 3p and 3d. But because we only have one electrons there, therefore we only try to do this 3s1 at the end of it. So let's try to apply this a bit method. I remember I gave you guys this particular exercise and teaching you how to do it with like looking at the subshell and orbitals. And generally, when we call them shell, we use a little symbol n to represent it. This little symbol n is quite confusing because when we learn shell, we use n equals to 1. When we try to learn calculation for doing number of mole, n is also be using. So that's sometimes to get you confused. But like remember when you look at shell, QM models, n is about shell. The subshell basically we have a quantum number L, and the orbit, the quantum number is the magnetic one, Lm. When you see n equals to 1, it has one subshell S, and in each subshell, you would able to have one orbitals for S, and each orbitals accommodate two electrons. If you have carbon as a 6 electrons initially, so you have 6 electrons altogether, the first 2 electrons need to go into 1s first. So this need to be first occupied. And then because we also have another 4 electrons left after we fill in the 1s, then we need to move on into the second shell. In the second shell, because we have two subshell, n equals to 2 means that you have two subshell. That is 2s and 2p. In 2s, you have one orbitals only, and each orbitals can occupy two electrons. S has a lower energy state, so we will put two of the electrons in that S subshell. After we fill in the first two electrons in the 1s and the second two electrons in 2s, we only have two electrons left for these particular carbon atoms. And these carbon atoms, we move on into the third subshell. When you try to look at third subshell, you have 3s, 3p, and 3d. 3s, 3p, and 3d there. One condition that we find out is when we try to look at subshell, 3p, like we normally imagine 4 would be bigger than 3. But there's a one exception that we learned in this particular course is 4s is the only 4 only subshell that belongs to n equals to 4 has a lower energy state than 3D. So if we have enough electrons, then we should go to fill 4s before 3D. But that one only apply when you go beyond 20, when you go beyond 18. But like we only have 6 electrons this time, so we don't really need to worry about anything else. Any 3 subshell for this one basically is all 0 because we don't really able to end up with it. And what happened when you try to look at 2p subshell? The 2p subshell is a bit bigger. It's bigger than s. For all the p subshell, it allows you to have orbital 1, orbital 2, and orbital 3. It means that you do have 3 orbitals in p subshell. For 2p1, 2p2, and 2p3. In 2p1, you can accommodate up to 2 electrons. 2p2, another 2 electrons. 2p3, another 2 electrons. So if you try to fully fill up 2p subshell, you should be able to do it up to 6. However, you only have 6 electrons, and 2 goes to 2s, 2 goes to 1s, another 2 goes to 2s. Then we will try to fill up 2p. For 2p, you will find that we try to do 1 electrons each first instead of 2, because the electrons basically repel with each other. If they have a choice, they would rather stay as like goes to different orbitals. So 2p1 has 1 electrons, then 2p2 has another electrons. And 2p3 would have no electrons because it's running out of it. And we call this 1s2, 2s2, and 2p2 as is the ground state of carbon atoms. So electron configuration for carbon, 6 electrons would be 1s2, 2s2, 2p2. So instead of saying 2p and then like you have like 2p1, 2p2, 2p3 right here, 3 orbitals, we can just add those 2 and put it at the top number to simplify that. But we know that at the end of the day, at the back of our head, at the back of our mind, that we know the electrons is placed as 2 different orbitals. Orbitals means the Lm number. Subshell is L. Let's go to have a look at the next one is the silicon. When you have silicon, silicon has 14 electrons. Basically, you put 2 electrons first in the 1s, and you put 2 electrons for 2s. Now we have 2p. 2p, we should be able to fill in all of them for 2p6. After 2p6, we know the 14 is more than 10. So you have another 2 electrons go into the 3s. Then it comes up to 1 and 1 again for 3p1 and 3p2. Now, if you have to write down the electron configuration for silicon, that would be silicon is equals to 1s2, 2s2, 2p6, 3s2, and 3p2. Just according to those, and the rest of them can be ignored. Someone is doing, yeah, I've got something kind of weird sound at the background. That's basically it's the aircon I've got at the back. So annoying. Now let's try to move on to the next one. Chlorine has 17. So for 17, we basically put 2 here, 2 there, 2, 2, 2, 2, and then 2, and then 2. Do we have this one too? Yes. 2, 4, 6, 8, 10, 12, 14, 16, 17. And the rest of them, we can ignore it. The first one here is 1s2, 2s2. Then we have 2p6. Then we have 3s2 and have 3p5. Come up to vanadium 23. When you have vanadium 23, so what we do is we put 2 there, 4, 6, 8, 10, and then 12, 14, 16, 18, 18, 20. And then we've got three d orbitals. D orbitals would be doing 1, 1, and 1. Can you see that? So for this particular diagram, it's very easy to fill up those electrons. It's like try to do it as like try to do all the way to the 3D. Then 3D has 5. So if you have 25, you rather put 1, 1, 1, 1, 1 for that. Just like the one that we looked at in the p orbitals. So at the last electrons, the last few electrons would be most of the time we need to pay attention to what do we do with it. So if we try to combine them, it's 1s2, then we have 2s2, done, join them together, 2p6, done, done, done. Then we have 3s2, done. Here is our 3p6. Then here would be the things that we mentioned before. 4s need to be filled first before 3d. As 3d is harder to reach, 4s has a lower energy level. The electrons would rather climb to 4s rather than 3d. 3d is too high for them to climb up to. So after they've got 2 electrons in 4s2, then the electron has no other option. They have to go to 3d. Then we have these 3 combined, 3d3. So what would be the vanadium V electron configuration? Is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and then 3d3 at the end. Right? Hopefully it helps you to understand what QM models the application for QM models. And this is like, the basic thing that we need to do. What I would give you this week, you will receive a little assignment before the end of the term. I'd like you to finish them and give it back. This is a multiple choice questions, all related to sort of like atomic theory that we've been gone through. That topic will be done. I'll give you another topic on the next video clip. So just have a go and search online. Thank you.